For those of you who are watching this recording later, we forgot the recording button, so talk to your classmates about the beginning parts. But for the rest of it, we are gonna have you. Okay, so we have the points we need. We have the step size, we have the initial values, or let's call them some value. Some x for which we know the y, right? And we have the limit. We are going to start from x and end at an x end. And we also have the function. This is where the Runge Kutta starts. What should we do?
Define a function with the expanded variables of like y naught plus the h times 1/3 of
So what Patrick, right? Patrick is telling me is that I need to write y as a function of all of the f hats, right? How should I do it in MATLAB?
It should be, well, I think you have to define it as, do you want to keep it as y, or do you want to define it as different, like yi plus 1, h plus 1?
The vector, it's the function is called y, right? Y of I is the value of y at point I, right? So that I part is just it's just pointing at the location. How should we do this? The first thing you want to do is to initialize this vector. I define this vector y. This is a vector that MATLAB doesn't know anything about. So we need to initialize this. And how do we initialize the vector? By zeros. So it will fill up the vector with all zeros. All of the arrays of the vectors is zeros. And then we give it a length. What should be the length of this y? The vector y.
The range of the x's divided by the subset. So that we have that many points.
Exactly. So the number of points we have here. How can we find out? How can we find those points?
X minus x start over h.
X end minus x start over h, right? Exactly. Or we can make it a little simpler. We can just say x is equals to, it's a function x equals to x start and goes to x end. Right, this is the command, which essentially is telling MATLAB this variable x starts from x start, goes to x end by these step sizes. And then here in the zeros, I can say that the length, right? Length of x. I can say the number of arrays I want in this vector is the length of array. Or I can define a dynamic array, which is going to take a long time to resolve because at each step you're adding a point to your array, right? It's going to take longer. Which, for a more complex function, you probably want to do that. So we have the function y, but it's all filled with zeros. What is the next step? The next step, as Patrick said, is to calculate the function at point I plus 1, right? But what is this I plus 1? How should I tell MATLAB that I want this I go from MATLAB starts from 1, right? Go from 1 to the number of points I have. Let's say I have 100 points. I want this I go from 1 to essentially choose one, do some calculations, go to the next one. Yes.
I equal like 1 semicolon
we need a loop, right? For loop, or we can have a while loop. And in that for loop, I'm going to define I that starts from 1 and goes to the length of x. And since we are only calculating yi plus 1, it has to go to that length of x minus 1. Right? We already have the first value of yi, right? We already know what is that value. Minus 1 then. Then how did we do? Right. What is the error I'm getting here? And maybe missing. Yeah, it is missing. Okay, so what is the next step? Do we need a? We don't even need this. What is the next step? In this for loop or outside of the for loop? Even outside of it. Let's do it outside of the for loop. I want to define the initial condition first. Y of 1 to the first point in y is equals to y initial. Does this make sense? This is the thing we want to do. And then here we want to calculate yi plus 1, which should be equal to yi plus, what is the function? H times 1/6. Let's call this, yeah, we can call it F1 plus 1/3 F2 plus 1/3 F3 plus 1/6 F4, and that's it. The next step is to evaluate, or let's first evaluate the F's. We don't want to cause any trouble for the software. So how can we calculate F1?
Real quick, won't those, the way you condition the F's, multiply it by the denominator, the denominator on each of those?
That's okay. It should not, but let's make sure that we have the correct thing. So let me add a parenthesis here. Does it work for you? Does it solve the problem?
It might work.
Do you want me to put these in the parentheses as well?
That's what I thought.
Okay.
How MATLAB works. We would need those first.
Sure. Okay, so how should we calculate F1? What was the formula we had?
Plug in the initial value onto the derivative.
Plug in the initial values in it, essentially the derivative at x, y, and y, exactly. So we're gonna get f xi, and what do we have here? We have x at I and y at I. That is how we evaluate f. This should be f. Why the f1? Yeah. Yes. Then what about f2? What time is it? What about f2?
xi plus half
xi plus h over 2 plus, right? Plus h over 2 and
yi plus h over 2
plus h, let's put this, or half multiplied by h multiplied by f1, right? Okay, thank you. What about f3?
Same, just F2 again.
F they're gonna have x of I plus h over 2, and for y part of it we're gonna have y of I plus half multiplied by h multiplied by f2 this time, and then f3 f4, I'm sorry, has to be f of xy. This time it is x of I plus h over 2 and y of I plus h multiplied by f3, right?
Isn't it just h at h over 2?
I'm sorry, that's correct. That is it, right? And then this should be it for the for loop. Yeah. It's telling me we don't need the parentheses for loop, so let's just remove this. Come from a C++ tradition, which is a little different. Okay, so this should give us the correct integration of 2x, right? But how can we make sure this is the correct integration of 2x? We are not going to go over all of the numbers, right, and compare them. What can we do here? We can just plot it, right? Plot x and y. That's it. And there are many options for this plot function, but at this point we are only going to write it. And let's hope for the best. Let's see if this runs. So we call it a in-class test or in-class example. The first thing it is asking us is to enter the step size. Let's go by point 1. Initial x 0, final x 0. A starting point, let's start at 0 again. And then the finishing point, let's do 10. As you can see, this plot looks like the x squared. Yes. Is there a question, Horton? You have a question?
No.
Okay. I hear something. Okay, do you have any questions? Did we all follow this? Yes. So for your homework, what I'm gonna do is that I'm gonna give you a simple equation. I'm going to give you the derivative. I'm going to ask you to find the analytical solution, which essentially means that you have to take the integral, right? It will probably be a double integral. Are we comfortable with double integrals? Okay, it's a simple double integral. I will give you the range, I will give you everything else, and you just have to write the MATLAB code. But also, there is one more thing for your homework that I want to give you, is that your book has these examples. Let me see if I can bring up the book. Has this examples. UofSC. Ebooks. Examples in which they have used the Runge Kutta method to evaluate the spring mass, a spring damper system, right? Example 1.17 is their analytical solution because we already have the analytical solution. Example 118 is their numerical solution, right? And they have separated the ODEs. They have come up with a system of two ODEs. And they have the code at the end of the book. So your second part of the homework is to go, and the code is a very complicated code, very hard to understand, right? So I want you to go over that second part of the code, just run it, make sure it runs, and comment each line. So I want you to tell me what each line is doing of that code. You don't need to write anything. You don't need to change anything. You have the example. You are gonna have the code at the end of the code is going to be at the end of this book, but I will include the code. So you just have to copy that code in MATLAB, make sure it runs, and comment different parts of it. Do you know you do know how to put a comment in MATLAB, right? That's it. So 3 questions. 2 of them are, all of them are very simple, to be honest with you. But there's one very simple programming part which we did, and the other parts, this part you just have to read through a code and understand it. Okay? Just have to tell me what each part does. Any questions?
Can you put the code back?
Sure.
Thank you.
And for the, did we talk about this? I don't remember. For the Runge Kutta part of the code that you have to write the code, I will give you that function. You have to take the double integral, and then you have to choose different step sizes, right? You have to make sure you plot all of those, compare your numerical integrations with regular analytical integration, right? And tell me which one is more accurate. Of course, the analytical solution is more accurate, but is the answer, not just more accurate, is the answer. But you have to tell me which one of the step sizes is giving you a better result and more accurate result. I will give you the choice of a step size and everything. You will have everything. You just have to write the code. Yes?
So, are you going to be posting on Blackboard whatever you just said?
Yes. Yeah, I will try to make the homework self-explanatory. So if you didn't come to class, you should be able to solve the problem. But if there was a question, you're always welcome to send me an email. Okay?
Another question. So, does this code only go from when you have your initial x as your start point to whatever the end point? Like, does it not go backwards? Like, if you want to go backwards, would you just subtract the h Or is there a different formula for?
It is a little different. Yeah, it is not just subtracting the h, right? It's a little different, but you can try. Why not?
I mean, I was wondering if the 1/6 the ratios stayed the same for like h times 1/6 f1 and 1/3 f2.
The ratios are actually that these are something that they are agreed upon. So different books have different ratios, different methods. So you can't really rely on these numbers. Most books you are using this, but we have more accurate Runge Kutta methods that use different methods. You have like a corrective method that uses a different method. So these different numbers. So any change may change these numbers. Any small, okay? Okay, if there is no other questions, we can stop a little early here today. And that will be it.